Thank you for joining this Phoenix Consultancy webinar on statistical process control. My name's David Clark. The aims of this webinar are to understand why control charts are important in improving services, to define common cause and special cause variation, and to understand why they need to be treated differently. You'll be shown how to create control charts using some of the tools from the Phoenix website and how to use them. And then we'll discuss some uses for control chart and some potential pitfalls involved in their use. Learning how to use control charts will enable you to evaluate underlying process or system capability and recognize whether it's stable and able to meet targets or specifications that are being set for it. You'll be able to reveal variation in the process or system, prove or disprove assumptions or even misconceptions about the system performance, drive improvement, and use data effectively to make predictions and help planning be more effective. It will also help you avoid data overload. Let's start with the fundamental question: why do we collect data? We collect an awful lot of data, but data should really only be collected if a signal within it would form the basis for action. Next, I'd like to discuss a couple of core principles for understanding data that I've extracted from one of Donald J. Wheeler's book, and he's a leading authority on statistical process control. The first core principle is that no data has any meaning apart from its context, and that leads us to three conclusions. Firstly, that we should distrust data that's provided out of context if we don't know how it's been collected or from what larger data set it belonged. Secondly, we should stop reporting comparisons between pairs of data, for example between one month and another, except as part of a broader comparison. And finally, use graphs to present current data values in context. It's far easier than looking at figures. The second principle that Wheeler's work gives us is that while every data set contains noise, some sets may contain signals. Therefore, before you can detect a signal with any given dataset, you've got to filter out the noise first. Failure to understand this principle can lead to mistaking signals as noise and vice versa. Whenever we've got data, we've got to go through a process that makes sense of it. So we have our input, our data, which we analyze, and that transforms it into our interpretation, which is our output. We need to be systematic about the way we process data in terms of collecting it and analyzing it, in order to make sure that our interpretation or output is reliable. Control charts are a good way of analyzing information in such a way that we can see the difference between signal and the background noise, and so be more reliable in the way we interpret data. Traditional data analysis tools used in management reports typically compare data with specifications or targets, and if these targets are unachievable, can sometimes drive gaming behavior in managers. We can compare to averages, but then there's a 50-50 chance of being up or down on the last average. And then finally we can compare to the last month or quarter or year. But it doesn't really tell us whether last month or quarter or year was a good year or a particularly bad set of results. And is the change noise in the system or a signal that we should be acting on? Managing an organisation on the basis of the monthly or annual report figures has sometimes been compared to driving your car on the basis of the information you can see in the rearview mirror. You shouldn't be surprised if it leads you to go off track from time to time. This webinar is about another way of looking at data, that is control charts, also known as process behavior charts and capability charts, and many improvement experts prefer the latter two descriptions, largely because the purpose of a control chart is to show how the process behaves over time and what its true capability is. To create a control chart, we start with a run chart, which is a time series, a plot of sequential values arranged in order of time or the sequence in which they occurred. So here we have a run chart, a sequence of values plotted in order, and along the center of the red line is the mean value of the points on the graph. In order to create a control chart, we need a run chart. We calculate the mean and add that as a horizontal line across the chart, and then calculate the upper and lower process limits and add those as horizontal lines above and below the mean on the chart. When creating a control chart, we make an assumption that the data will have a roughly normal distribution, although they are useful for data that does have a skewed distribution, providing that's not too great. As you're aware from statistics, in a normal distribution, just over 68% of all points occur within one standard deviation of the mean value. Around 95% occur within two standard deviations of the mean, and less than 1% of values are outside three standard deviations either side of the mean. The upper and lower process limits approximate to 3 standard deviations either side of the mean, although the way that they're calculated is slightly different from traditionally used in statistics. Standard deviation is also sometimes referred to as sigma. In this illustration, you can see that the control chart has a histogram of the data stuck on the side to visually show the relationship between 3 standard deviations from the mean and the upper and lower control limits or process limits. I now want to briefly run through how control limits or process limits are calculated from the data that you have. For those of you that don't enjoy mathematics, this won't last very long, but it does give you an idea of how they're calculated and how they're able to be calculated on such small numbers of data points. Please don't worry about the mathematics if you don't enjoy it, because all the calculations are performed within a spreadsheet that's available on the Phoenix website. The first step in analysing the data to create a control chart is to use the individual data values to calculate the mean. Another set of data is created by working out the difference between 2 consecutive readings throughout the data series. This is always marked as a positive value, and this is called the moving range. The next step is to calculate the mean of the moving range data. One standard deviation, or sigma, is calculated by dividing the moving range by a constant, and that's usually looked at from a statistical table chart. So the upper process limit, or upper control limit, is the mean plus 3 sigma, 3 standard deviations. The lower process limit, lower control limit, is the mean with 3 sigma, 3 standard deviations subtracted from it. This methodology allows a control chart to be constructed with as few as 20 data points, although 50 is better. If one of your initial data points is out of the process limits, it's worth considering excluding that point from the calculations. Standard deviation does not refer to the same formula in Excel or on calculators. This is a different methodology for deriving that value. 20 data points will therefore produce 19 moving range values. So that's enough of maths for now. And as I said before, you don't need to do the maths, because all you need to be able to do is cut and paste into the spreadsheet available on the Phoenix website. I'll be running through how to use the spreadsheet a little later in the webinar. So that's how you get a control chart as shown here, which has a run chart with sequential values, a central line marking the mean, an upper line marking the upper process limit or a control limit, which is 3 standard deviations from the mean, and a lower line marking the lower process limit or lower control limit, which again is 3 standard deviations or 3 sigma from the mean. The control chart that we can see here shows 23 data points collected as a time series over 23 months. The central line is the mean of the data points, and we've marked the upper and lower process or control limits. In this example, all the points lie within the control limits, and we can say that this control chart shows the process to be predictable or in control. If a process is behaving predictably, that is, it is within control, we can make the following assumptions. 99 to 100% of the data points will be within 3 standard deviations, that's 3 sigma, on either side of the mean. 90 to 98% will be within 2 sigma, and 60 to 75% of the data will be within 1 sigma. In practice, the first of these, the 3 sigma, is used to mark the upper and lower process limits. If the process is behaving predictably, points outside the control limits should be very infrequent, and their presence is likely to be a signal of something happening to the process that's starting to push it out of control. Variation within a process can be classified into 2 types. In a predictable process, that is a process that is in control, the data points lie within the upper and lower control limits. This is often referred to as common cause variation and is intrinsic to the process. Because the variation within a predictable process indicates its capability, improvement of a predictable process requires changing the entire process rather than trying to seek assignable causes for each of the data points. If the process or system is behaving unpredictably and is out of control, data points will be present beyond the upper and lower control limits. These are usually a result of special or assignable causes that are extrinsic to the process. Improvement for an unpredictable or out-of-control process usually starts with trying to address the special causes for this unpredictable variation in order to bring the process into control and make it predictable. Here we have an example of a control chart showing some special cause or assignable cause variation. 2 of the points are above the upper control limit, and it's likely that root cause analysis would be able to demonstrate a special or assignable cause extrinsic to the normal process In addition to the presence of points outside the control limits, some other rules have been developed to indicate the presence or the likelihood of special cause variation affecting the process, and I'd like to run through some of these now. The first rule is one we've already covered and the most obvious, which is any point outside the control limits is likely to indicate special cause variation. And here we have a real-life example. This is from some work done by the NHS Modernisation Agency trying to improve the lung cancer referral pathway. And as you can see, there are some points above the upper control limit in which there were excessively long waits, and it's likely there were assignable special causes for these very long waits. The second rule is that 7 points above or below the centre line, that's the mean, are likely to indicate special cause variation occurring within the process. Rule 3 is the presence of a cyclical pattern or a trend pattern within the data, and this again usually indicates something extrinsic to the process influencing it. Rule 4 may be less obvious to spot. This is when less than 2/3 of all the points fall outside a zone marked by 1 sigma, 1 standard deviation either side of the mean, or more than 2/3 of all the points fall into this zone. It is essential to understand the difference between special cause and common cause variation. As I said earlier, common cause variation is intrinsic to the process, and in order to reduce it, the whole process needs to be improved and changed. On the other hand, special cause variation is usually extrinsic to the process, and in order to improve it, we need to address the special causes, in fact the root causes of the special causes, in order to bring the process into control and make it more predictable. Failure to distinguish between common cause variation and special cause variation, and so applying the wrong approach, can actually make things worse if special cause variation were addressed as though it were common cause variation, or if outlying points within a predictable process due to common cause variation were each investigated as if they were due to a special cause. For further information on how to investigate special or assignable causes, you could visit the Phoenix website and see the root cause analysis webinar. I'm now going to talk you through creating a control chart using your own data with the Excel template that's downloadable from the Phoenix website. So firstly, download the template and open it. If prompted, click Enable Macros because this is required in order to allow the functions to operate properly. Next, save the file under a new file name appropriate to your project. When you open the file, you'll see this welcome screen. Next, click on the tab at the bottom of the screen marked Info. This will open that data sheet. In the box at the top of this sheet, enter in the top box the name for your control chart. In the next box, what you're going to have along the x-axis, for example, sequential patient number or date. And on the third box from the top, what you're measuring on the y-axis. This is the main variable that you're looking at, so it could be turnaround time in hours or days or percentage defects. In essence, this box just contains what you're measuring and the units that you're using to measure it. Next, you need to click on the tab at the bottom of the screen marked Data. This will open this data sheet. There are some explanations of what to do on the right-hand side of the page. There are 2 columns. In one, enter the sequential patient number or date. In the second column, enter the measures that you've collected. It is essential that they are entered in the sequence in which they were collected, whether that be the date, the time, or the order in which the patient or the specimen arrived. It's fine to cut and paste data into the chart so long as the sequence is unaltered. Now click the grey button on the left hand side of the page to generate your SPC chart, and that will create a control chart. Then click the button at the bottom of the page marked Your SPC Chart, and that will take you to the sheet in which you can view your control chart. The control chart will look something like this and can be copied and pasted into another application such as Word. This is a chart I created looking at data on the breast resections that I reported over a period between June and November 2010. As you can see from the data, there are upper and lower control limits, and there's a central line marking the mean at just over 5 days. There are 2 specimens that took longer than the upper control limit at 9 days, and this was a result of special cause variation in the process. Both of these cases, when I investigated them, were cases in which I had to go back to the specimen to take additional sections, and that delayed the reporting of these cases. What kind of data can we use for a control chart? Well, firstly, it has to be sequential. It has to be in a time series. Secondly, It has to be numerical. There has to be a measure of some kind that we can put into the chart. And that could be in pathology or radiology, the turnaround time for reports in days or hours, or the percentage of defects that we get within a certain time period. They can be adapted to be used for rare or infrequent events, but this requires a slightly different type of analysis, which is more specialised, measuring, for instance, the number of days between events. However, I'd recommend that you got assistance from an expert if you were trying to use this technique for those kind of rare events. I'd now like to ponder the question what to do if this kind of thing happens. That is, you have a service specification marked in blue here at just over 60%, but the process capability demonstrated in the control chart shows that the process is clearly incapable of meeting that specification or target. When it comes down to it, there are only three ways to meet a target like that. The first is to improve the system capability in order that it will meet the target reliably. The second is to distort the system in some way such that it appears to meet the target, perhaps by adversely affecting another part of the wider system. And the third is to distort the data. So the danger of arbitrary targets that don't take into account process capability as measured through control charts is that in the absence of any ability to improve the system, managers are forced into distorting the system or distorting the data in order to meet a target. Clearly, the only way to really meet a specification and satisfy user or customer demand is to improve the system, and control charts are incredibly valuable in measuring whether a service improvement project has actually improved the system. Firstly, because they can detect whether the mean performance has improved, and also whether there's been any improvement in variation, and whether the new system is in control or predictable. The control chart you can see here is an example of how they can be used to detect whether a change is actually an improvement. There have been two improvement activities in this control chart of turnaround times, and after each one the mean and the upper and lower process limits were recalculated to see whether they had actually changed from previously. It's quite clear that each of the two improvements improved the mean performance of the system and lowered the turnaround time. There were still some out of control points after the first improvement event. However, by the second improvement event, the upper process limit had actually fallen below the mean performance of the system prior to any improvement activity. Used in this way, the control charts are incredibly valuable in detecting whether a change is actually an improvement in the system, and also monitoring the system over time to see whether there's been any deterioration in performance. So I'd like to sum up what we've talked about in this brief guide to control charts and statistical process control. Firstly, control charts are very valuable because they put data into context and show how the process will behave over time. They show the true process capability and how it behaves, and reveal whether it can meet a target specification. They show variation and help delineate between common cause variation and variation that's due to extrinsic special causes. And also they're invaluable in helping guide improvement in detecting whether a change has actually improved the system and then monitoring the system performance and behaviour over time. Thank you for listening to this Phoenix webinar. Please visit the website for any of the tools mentioned in the webinars.